Hello everyone, welcome to the another class of fundamentals of particles and fluid solid processing. Today we will be seeing and learning this particle size distribution. Now, why this particle size distribution is essential? Because you can now understand that we are talking about a collection of particles or a mixture of particles, a bulk material handling in industrial cases. Now, in those cases, although we have previously discussed about a single particle characterization, but now it is essential to understand that handling of multiple particle or millions of particles together is what happens at the industry level. Now, that means if you have a storage of tons of these fine particles or different size particles, how do you quantify that bulk material or the storage of material by a single number? So, it is essential to quantify a system that consists of a wide range of particle size by a single number, so that people can understand that okay, we are dealing with this sample, and it can vary from the sample to sample. So, very simple way to represent that is what I have shown in this slide by this frequency distribution or cumulative mass fraction curve. So, this figure is essentially shows you that this x axis is the particle size and y axis is what we call the cumulative mass fraction, or let us say the mass fraction. Now, here you can see that the mass fraction of a sample, the sum of that will be essentially total 1. Now, this curve shows that you take a certain size of particle, and below that whatever is the size, the mass fraction of that particle, you start plotting those values. So, for example, you have let us say till 100 micron of particle, and then from 0 or let us say from 1 micron, 2 micron, 3 micron, 10 micron, 50 micron, etc. So, this type of or this size of particles you can measure. So, let us say whatever the mass of the particle below 500, let us say 50 micron size, you can have its mass fraction. You plot that point. Similarly, whatever the particle mass fraction is there below 70 micron, you can weigh that, you can find out the overall mass fraction for that size, and you can get another point. So, by connecting these points, you can basically come up with a cumulative mass fraction curve. Now, what happens from this cumulative mass fraction curve? Once you have such kind, this is a typical example I am showing here. So, what happens here, that once you get such curve, which essentially goes to maximum value of 1, because the total mass fraction cannot exceed the value of 1. Now, here once you draw such curve, you find the median of this graph. How do you find the median? You take the 50% of the total sample, and then you draw a horizontal line, you find out where it intersects, and you get a value at the x axis, which is the median of this sample. So, if you have a sample that consists of particle size up to 100 micron and has such cumulative mass fraction curve, you find the median and you find that its characteristic dimension of the particle, or by the number that you can designate this sample, is by around 45 or let's say 44 micron. So this is a single number we have deduced, by which we can define this whole sample by a single number. So this is one of the easiest example that can happen. And also such a curve or a plot, when we do, we call this as these are the cumulative mass fraction curve, okay, or let's say the size frequency based on cumulative mass fraction. The other size frequency can happen when we take the slope of each and every point of this curve and we plot, which comes up like something this kind of a plot, which called the differential frequency distribution. So, and here in the y axis you can see that this is the slope of the previous graph that I have shown. So, this parameter df by the frequency, or let's say this is the dx, we can have fx, a function of x, which we can say this is the differential frequency distribution. Now, in this case, the mode which represents the most occurring number, or here in this particular case the most occurring size of the particle in that sample, is represented by the mode value of this whole plot. Okay. So, this peak basically represents, this is the mode of this graph. So, again, so this kind of a number, again similar to 44 or 45 micron is, so basically we come up with the size distribution, which can be plotted in both the way. One is directly by cumulative mass fraction plot, the other way is to find the differential frequency distribution plot, and by the median and mode we can find out a single number by which we can characterize that sample or that whole range of the size distribution. We can designate one number to represent that collection of particles. Now, here this is again, this is a representative image, a representative graph, where only one single peak we have shown. Now, there can be several peaks in a mixture or a collection of particles. Now, those peaks basically represents that the maximum number of particle in that size range it is occurring in that sample. So, typically what happens when we crush larger particles, there are two peaks we can see in such graph. Okay. One peak is for the material or its characteristics, the other peak represents the equipment by which we are crushing that particles, that is a characteristic peak for the equipment. So, these are the two major peak we can have, or dominant peak we can, or let us say the visible peak we can see ideally when we crush larger size particles. One represents for the material and the other represents as a characteristics for the crushing or the grinding equipment. So, to sum up these two slides, this one and the previous one, is that the difference is, this is a cumulative mass fraction of a particular, or let us say a given size range. When we take slope at each and every point of this curve and we plot it like this, again with the particle size, we get this distribution. So, the differential or the derivative of this previous cumulative mass fraction curve is this differential size frequency distribution curve. So, this is the relation between these two graphs. So, we have size distribution curve. Now, as I said, we have to have a mean, or let us say a single number, like we have seen in the previous two slides, one by median and the other by mode. We got one number, single number to represent that sample. Now, those are not only the practice, there can be several ways to find out a single number to represent the mixture that consist of wide range of particle size. For example, mode and various means. The example of mode we have seen. There can be various means like the arithmetic mean. We simply do that by averaging. There can be geometric mean, there can be harmonic mean, and etc. There are several statistical means are available to find out what would be the appropriate representation of that sample by a single number. Now, for a particular or a given size range, there can be different means. Now we can understand. So, which one we should consider or how we should choose, we will see that in the coming slides and in the coming class as well, that the property under consideration actually influences this choice of this mean, and how that happens we will discuss it slowly. So, let me give you an example at this moment, is that the property under consideration influence the choice of means. That means that in which application you are looking for the mean for that particular sample or the collection of particles. For example, there is a flow through such particles, that is equivalent to flow through a packed bed of particles. In that case, which mean you should use? Let us say, then you can apply Koenig-Karman equation, Argan equation for such applications, and there you have to put a equivalent d or the diameter. So, what would be that equivalent d? What is your consideration? We will see that slowly. So, before that, let me tell you that what are the different types of means that statistically or most popularly are used in such determination. So, let us say if you have a function px, okay, and the average value, the mean value is this one. So, this mean basically defined by this formula. This is the definition of having an average value of a function. Now, if this this px is x, then this definition gives you the formula for arithmetic mean. Now, here you must recognize that this integral 0 to 1 df is basically 1, because again if I go back to the previous curve, you can see that the total mass fraction, the cumulative mass fraction is 1. It cannot go beyond value 1. So, ideally it is 1. So, basically the average or a mean of this parameter px is determined by this function, where if px is x, then you get arithmetic mean. If px is x square, this mean is called quadratic mean. This px bar, this is the average value. If px is x cube, this definition gives the cubic mean value. If it is log x, it is the geometric mean, and if it is 1 by x, it is called the harmonic mean. So, we can understand that there can be several means for a particular function. This function is nothing but the size distribution curve. That size distribution curve can be represented by a function such as px. Once we feed that with the proper value, we get a appropriate mean value. So, by doing this, you should understand that a given size distribution can yield significantly different means. Okay? A particular curve can give you different mean values that are significantly different values. So, for example, a given there is a given size distribution, you found that its arithmetic mean is x1, geometric mean is x2, and harmonic mean is x3, and these are totally different values, distinctly different values. This can happen, and two different size distribution can have same arithmetic mean or media. Okay, This statistically you can understand that when there are two different size distribution graphs, but due to the central modal nature of those graphs, you can have similar value of the arithmetic mean or the median. So, selection of appropriate mean becomes important in both the cases. Both the cases means that for a given size distribution, as I told earlier, you can have different means, but which mean to choose? And there are two different size distribution, two different sample, but its arithmetic mean or media coming out to be the same. So, what it leads to that if you choose a different mean, your design and all other subsequent steps can be wrong or will be wrong, and it will create some inappropriate design. So, the selection of appropriate mean for a particular size distribution is important, and to identify that for different size distributions a particular mean which will be representing differently in both the cases, that is also equivalently or similarly important. So, now coming out, let us say we look into the mean particle size. Okay. So, how to calculate such mean particle size? We have seen theoretical part. Now, let us see that how really one can calculate mean particle size for, from a collection of particles or a sample which has different size of the particles. So, let us assume you have unit mass of particle where xi is the mass fraction of the ith component or the ith component of the size. So, let us say you have a size 1 particle that has a mass fraction of x1. Okay. So, x1 is nothing but the number of particles which is n and k d cube, where k is a constant that depends on the shape of the particle, and d cube is basically k d cube. This whole term is basically represents the volume of that particle. Okay. Volume is the linear dimension to the power q. So, that is represented here by a dimension called di, and k is a constant that depends on the shape. So, now you understand for a spherical particle this k value is basically pi by 6. For square, this for a cube this k value is 1. So, it is written for a generic purpose. So, number of particle, the volume and its density. So, so this and its density, it is not the cube. Okay, that is my mistake here. So, here that means we can write Ni is nothing but 1 by rho k and xi by d cube. So, this thing, this conversion is basically important in this case. So, from mass fraction to the number distribution. So, number of the particle, ith means the size 1 particle. So, similarly for the size 2 particle, it will be x2 n2 and equivalent diameter of d2, and this summation of mass fraction is always equals to 1, which is rho k and this summation of this value that comes from this expression. So, now if we try to represent the size distribution by a continuous function, then quite naturally dx is k d to the power d cube rho and number differential element or the differential numbers, and dx by dn becomes rho k d cube, and this integral, which is basically the mass fraction, the summation of mass fraction from 0 to 1 is basically 1, and it is giving this expression in a continuous mode. So, coming to the mean size calculation based on certain criteria, because we can understand that this mean size can be based on a certain parameter like the volume, like the surface, like the length. We will be discussing this sequentially. So, volume mean diameter, if we try to define for a collection of particles, then we can understand that this is the definition where d 0 to 1 and this is the mass fraction from 0 to 1, which is basically this denominator is 1. So, this definition gives us the volume mean diameter of that sample or the collection of particles, which if we try to write in finite difference form, it is the summation of di xi divided by the summation of xi, where again summation of xi is 1. So, it is basically this expression, which is nothing but the mass fraction of a certain size component multiplied by its diameter. Similarly, mean volume diameter, you have to now look into the adjective that we are putting mean after a certain word. Here it is the volume mean diameter. Now we are talking about mean volume diameter, which means let us say we have this d prime v is the mean volume diameter of that collection of particles and it is uniform. Now, since volume is conserved for, because this mean we are defining based on the volume, so the volume is conserved, volume should be identical. Now, by that the definition becomes k d prime v cube, which is the volume multiplied by the number of particles, is basically the summation of individual component. So, by doing this we can find out the mean volume diameter as this expression. And when, like in the previous slide, we have seen that the relation between n and x. So, if we now replace this ni with xi, which is the number to the mass fraction, we can have the expression of d prime v, which is the mean volume diameter, as this expression, which is 1 by summation of xi di cube, its root over 3 root of this. So, similarly, if we see the surface based mean sizes, like in the previous slide we have seen volume based mean sizes. Now, this is the mean size based on the surface. So, surface mean diameter, or it is also popularly called the Sauter mean diameter by the name of the scientist Sauter. It is defined as this way, where again this ni is the number, d is the diameter of that sample, s is the surface area of that particular ith sample or the ith size particle, divided by summation of this parameter. Now, here also this surface we can write like the volume as a certain constant multiplied by the linear dimension square or the di square. So, by doing that, like in the volume we have mentioned that it is the linear dimension cube. So, surface is linear dimension square and with a constant parameter that changes with a different shape. Here we are designating that as k prime. We can have this expression, that is 1d was there already and s is related with the k prime di square. So, ni k prime di cube, and at the denominator similar expressions, but here it is di square. So, since this is a constant term, it is eliminated from numerator as well as the denominator. So, we get this expression as the mean diameter or the Sauter mean diameter, surface mean diameter. When we again replace this n with the expression of x, we get this value, which is So basically, again, let me go back those who are not getting this point, that this is the expression that we have seen before coming to that expression. So Ni and Xi. So we are now replacing wherever the number, and this is the mass fraction. So this is the relation between the mass, the size distribution by number and size distribution by mass fraction. So similarly here also, when this Ni is replaced by the expression of X, we get this dimension. So here we get the surface mean diameter or the Sauter mean diameter. Here again it is the mean surface diameter. So here we get, like the volume we have mentioned, if the mean surface diameter is designated by d prime s, we can write this expression that, let us say the sample has mean surface diameter of d prime s and it is uniform throughout the sample, and the surface area is conserved. So we can write this expression for each and every ith size particle, and then we can get this expression from this step, where again if we replace this number by the mass fraction, we get this expression for the mean size diameter. For the length based mean sizes, length mean diameter is defined by this expression, where this is Ni and Di square. Now length is basically proportional to the linear dimension. So that is why it is we have eliminated, there is no necessity of expressing that with another proportionality constant or the constant value, and it becomes this expression when it comes for the number distribution, and this is with the mass fraction distribution. For mean length diameter, similar kind of definition we have put, that if d prime L is the mean length diameter of that sample, it is multiplied by the summation of number of ith particle is basically equals to the total Ni Di, and we get the mean length diameter by number distribution, and this is the extreme right side, this one is the by mass fraction distribution. So basically what it tells, that in the three cases that I have shown, is the one is volume based mean sizes, where we have expressed that in terms of xi di, which is the mass fraction and the diameter of the respective mass fraction. Here also, but it is mean volume diameter. So do not confuse with volume mean diameter and mean volume diameter. This results in two different expressions. Similarly, surface mean diameter or Sauter mean diameter versus the mean surface diameter, and length mean diameter and mean length diameter. So these are the 6 variants we have seen, and these are different in expression, as well as this can yield different values for a given size distribution. So how these expressions will be used, we will be seeing when we will look at and worked out example. What will happen, that for a size distribution you will be given with this xi and the di values, or let us say the ni and the di values. So let us say you have 100 numbers of 1 micron particle, 50 numbers of 200 micron particles, 70 numbers of 30 micron particle. These kind of tables you will be given, and then you will be asked to calculate that what is the mean diameter of that based on a certain criteria, either it is a length or volume or surface. So we will be seeing that in the coming classes, and that's all for now. With this, I would like to thank you for your attention.